Welcome to Lecture 6.1, Introduction to Fourier Series. In this lecture, I'm going to show you what a Fourier series is, and I'm going to derive the formula for the coefficients. I should mention that this is not going to be a 100% rigorous mathematical derivation, but rather I'm going to appeal to your intuition so you understand what these things are and where they come from. And the ideas in this lecture are going to come up repeatedly in lectures later in this series. Okay, so here's some motivation for the concept of a Fourier series. Every well-behaved periodic function, and by well-behaved I mean piecewise continuous, can be decomposed into sine and cosine waves. So let me give you an example of this. So here's a function. This is not continuous. Here's another function. This one is continuous, but it's not differentiable. It's a sawtooth wave. These things are piecewise continuous functions. They don't look like they have sine and cosine waves in them because this thing has discontinuities and this thing has corners. But we can nevertheless write these functions as infinite sums of sine waves and cosine waves, those really smooth functions. And that, to me, that seems remarkable. Coming from a mathematician standpoint, that seems too good to be true. However, every musician can tell you that, or every sound engineer can tell you that this is obvious. Of course, these things are just sound waves, and the fundamental frequencies, or the harmonics, sound waves are just these things, and you put them together the right way, and you get square waves and triangle waves. So an analogy for the math behind this, and this will seem out of left field, but stay with me on this one. I think you'll like it. So Rn, this is my notation for n-dimensional space, n-dimensional vectors. So Rn is a set of vectors. So when we have a set of vectors, we can freely add and subtract vectors. We can multiply vectors by scalars. We can measure the length of vectors, and we do that using the dot product. The length of a vector v is just the square root of v dot v. This is just the Pythagorean theorem. If this looks kind of weird, the length, here's an example, the length of the vector 3, 4 is, you take the square root of 3, 4 dot 3, 4, and so what is this? This is just the square root of 3 squared plus 4 squared, which of course is 5 squared. So this is the Pythagorean theorem. It allows us to measure the lengths of vectors. And I'm going to write it in terms of the dot product, which is how it's formally written usually. And we can also measure the angles between vectors. If we have a vector v that goes this way, let's say this is a v and we have a vector w, this may not be something that you've seen, or you've likely seen it and forgotten this or not noticed it. This is like the law of cosines, or one form of it. So the angle between v and w can also be expressed in terms of the dot product. It's the inverse cosine of this thing here. And this is not something you need to know for this class, this formula. Just recognize that. What I want you to take away from it is the length of a vector can be expressed using the dot product, and the angle between two vectors can be expressed using the dot product. Finally, we can project vectors onto unit vectors. If we have a unit vector, or n for normal vector, let's say this is n, and we have vector, this is v, then we can project v onto n, and what we do is that gives us this vector down here. So we take n and we take the line through n, and this vector right here is we say it's the projection of v onto n. And that can be done using the dot product as well. It's this formula, and we'll go over this in the next slide. We can actually project vectors onto non-unit vectors by normalizing them. I'm not going to get into this. Basically, I want you to take away that with vectors, we can add them, subtract them, and multiply by scalars. We cannot necessarily multiply vectors together. That's not always possible. In R3, the cross product works, but that does not work in an arbitrary number of dimensions. So with vectors, we can add, subtract, and multiply by scalars. And then once we introduce the dot product, we have geometry. We can measure the lengths, the angles, and we can do projections. Okay, so to motivate our derivation of Fourier series, I want to ask you some very simple questions about geometry in R2. So the standard unit basis vectors in R2 are just E1 and E2. There are these things right here. And I'm going to let V be this vector, 4, 3. So let me ask you these questions. First of all, how long is V in the x direction? So think of V as like a velocity vector. So when I say how long is it in the, actually let me draw that longer because I can. So when I say how long is it in the x direction, think of it as if you're running in this direction or you're in a boat, how fast are you moving in the x direction? Well, that's easy. That's just 4. And how long is it in the y direction? That's 3, right? But it's a little bit harder if I say how long is it in the northeast direction. What I'm really asking there is, let me first mark off this axis. So this is 4, this is 3. Now this is my unit basis vector. This is E1. And this is my basis vector E2. So how long is this vector V in the northeast direction? Not quite so clear. Although we know it should be large because that's almost the same direction as this. Okay, so where does this 4 come from? 4 really is coming, all that is just V dotted with E1, the standard unit basis vector in the E1 direction, or in the x direction. So if you take that dot product, you just get 4, 3 dot 1, 0, and that's equal to 4. That's all we're doing. So how long is V in the y direction? Well, that's 3. Not surprisingly, that's just V dot E2. You take the standard unit basis vector in the y direction and take the dot product of V on that. And that is just 4, 3 dot 0, 1, and that's equal to 3. Geometrically, what you're doing is when we get 4, we're taking the dot product, and that just drops the perpendicular and it measures the length of the projection, which is this. And when we take the dot product of this with E2, that projects V onto here and measures the length of this vector. So if I were to ask how long is V in the northeast direction, well then that means that so let me draw the unit circle here. So what we're really saying is let's take the unit basis vector in the northeast direction. That's this vector. Let me call that N. And then we know what that is from basic trig. That's just root 2 over 2, root 2 over 2. And what we're really saying for this third question is we're asking what is V dot root 2 over 2, root 2 over 2. We have to normalize this, otherwise it doesn't work. So again, what is this like? So let's take the line that goes through this, and let's drop a perpendicular, and then the answer is going to be whatever length that is. So it's however long it is from here to here. And then you're going to see this is going to be approximately 5, because we know this has length 5, Pythagorean theorem. This is V. Okay, so this thing is just, it's 4, 3 dot root 2 over 2, root 2. I'm sorry, I've switched my notation. Let me cross this. Let me write it like this. So this is 4 over 3 times root 2 over 2, root 2 over 2. Yeah, so I started writing vectors vertically like this, and then I wrote this one as an ordered pair. Sorry about that. But anyways, what this is that this is 7 halves root 2, which is approximately 4.95. I did that in advance. So this is 4.95. And again, that makes sense. This is, think of this as like a runner running in that direction. He's running 5 miles an hour in this direction, then in this direction he's really going 4.95 miles an hour. And think of this as like the gradient or the velocity vector, and we're projecting that onto different coordinate directions. You've seen this in Calculus 3, or vector calc. This is the directional derivative. Okay, so the last thing I want to emphasize here. So far, you should think that if I want to measure a vector in certain directions, I do the dot product. And finally, let me take this vector v, which is this guy here. No, sorry, it's this one here, 4, 3. And I want to decompose it. I want to write it as a sum of something in the x direction and something in the y direction. Well, obviously, that is just 3 times e1 plus 4 times e2, right? 3 times 1, 0 plus 4 times 0, 1. Oh, I'm sorry, other way around. Yeah, that's not right. So it's 4 times e1 plus 3 times e2. Had that backwards. And so this 4 is not just random. That 4 is precisely v dot e1 times e1, and the 3 is just v dot e2 times e2. So the big idea here is, given a vector, if we have your perpendicular or orthonormal basis, like e1 and e2, we can decompose that vector into those directions. 4 times e1 plus 3 times e2. And this 4 and the 3, these are just dot products. These are projections. So this is what we're going to be doing with Fourier series. We're going to have a periodic function f of x, something like a square wave. And so it's going to look something like this. And we're going to abstractly think about functions as vectors, because we can add them, we can subtract them, we can multiply by scalars. And so what we want to do is we want to write this function as a sum of cosine waves and sine waves. So we're going to have infinitely many of these things. So we want to decompose this function into sine waves and cosines. But to do that, we need a dot product. So we define this strange dot product in this on this space of functions. And it works. It amazingly works. It makes the sine and cosine waves perpendicular, like the way these are perpendicular. So we can take any function and we can write it using our sine and cosine waves, and the formulas for an and bn, these coefficients, they're just dot products. So an is just going to be the dot product of f of x with the cosine of nx for our strange version of dot product. So that's what we're going to do next. Okay, so here's a quick definition that we need. A set of vectors is orthonormal. And before I finish the sentence, let me say what this means. This means two things. This means unit length, in other words, length 1, and perpendicular. So unit length, that means that the length of vi, which is just the square root of, v. I'm going to start omitting the hats on here. So vi is equal to 1. And perpendicular means that vi dot vj is equal to 0 if I and j are different. So we can actually summarize. So here are the two conditions. We can actually encapsulate both of these conditions in a single statement, which is right here. vi dot vj is 1 if these are the same thing. So in other words, any vector projected onto itself has length 1. That means unit length. And vi dot vj is 0 if they are different. So you should think about orthonormal vectors as just being perpendicular. Like this is like v1 and v2. If you're in R3, that means something like this, and these are perpendicular. So this might be v1, this might be v2, this might be v3. That's what orthonormal means, and I want you to remember this definition. Why do we care about that? And again, from the last side, the big idea is, let's take a vector now. Let me take v to be 5, 4, 3. I can write this as 5 times E1 plus 4 times E2 plus 3 times E3. And remember, and again, my unit basis vectors now in R3 are the same as what you would expect. They are EI is 0 everywhere and 1 in the ith coordinate. So again, this thing here, this 5, 4, and 3 is just the projection of V onto E1. So this is V dot E1. I'm going to omit my hat here. So this is V dot E1 times E1 plus V dot E2 times E2 plus V dot E3 times E3. So big idea, when we have an orthonormal set of vectors, we can decompose any vector into those vectors using dot products. Okay, so let's go back to functions now. I'm going to let p sub 2 pi be the set of all 2 pi periodic piecewise continuous functions. So by 2 pi periodic, I don't necessarily mean the fundamental period is 2 pi, I just mean they repeat every 2 pi. So that is, p sub 2 pi is the set of all real valued functions where this holds. F of x plus 2 pi equals f of x. That means it repeats every 2 pi, and f is piecewise continuous. So for example, things like sine waves and cosine waves are going to be in there. There's also going to be things like triangle waves. There are going to be discontinuous functions like square waves, something like this. There's going to be things like this. So here's the first key point I want you to think about. This is abstractly a vector space. It's a set of, think of these things as vectors. Now, what is a vector? A vector is a thing things that we can add together. We can subtract. We can multiply by scalars. That's all we need. We can add these functions together. We can subtract these functions. We can multiply these functions by scalars. And if we do that, we still get a 2 pi periodic function, piecewise continuous, just like this. So abstractly, that's what math is. It's abstracting some patterns you see. This is a set of vectors. So what we want to do next is we want to define a geometry on the set of vectors so we can project vectors onto different vectors. So here is how we define that dot product. So the word dot product is special. It's the dot product that you've learned in high school. It's taking two vectors, but the concept of a dot product generalizes to something called an inner product. So the word inner product just is a generalized dot product for spaces that are not Euclidean, r to the n. So the inner product on this space is defined to be this. In other words, if I want to take the dot product of f and g, I'm going to define it to be this thing here. And you can think about it, this is sort of like a continuous version of the dot product, right? The old dot product is like, this is ABC times DEF, then the old dot product is what do? You just multiply each component and add them up. Well, that's what you're doing here. You're multiplying f times g at each point, and you're adding it up just in a continuous fashion. And this is some constant that is needed for technical reasons. Okay, so this defines length, an abstract notion of length in here. So, or I should say magnitude. So this defines length, or if you prefer, magnitude. Of not just vector. Well, recall from in Rn, the length of v was the square root of v dot v. So in our setting, the length or the magnitude of a function f is just the square root of f dot of this inner product, which is the square root of 1 over pi, negative pi to pi, f of x, g of x. So what does this mean physically? That's not quite so clear. Okay, so great. Now what? So if only we had a set of orthonormal vectors that we could project our functions onto with respect to this newfound inner product, something that took the place. In R3 we had E1, E2, and E3. If only we had something like that for our periodic functions. And amazingly we do. Here's an amazing fact. With respect to our inner product, once we define this, we get a notion of length and angles and geometry. This set here is an orthonormal basis. So that means it's a basis, meaning every periodic function can be written using these things. So yeah, I know this one's a little weird, but you'll see why in a few lectures why this thing is funky like this, but it has to be renormalized. Maybe I'll say more about this in this lecture. So this is the basis. In other words, any periodic function we can write using these, but it's also orthonormal, and that's the incredible fact. And that means that when I say it's orthonormal, that means if I take the dot product of any two of these functions, if they're different, I get 0, otherwise I get 1. So for example, if I take the dot product of cosine of n, I should be switching to inner product. So cosine of nx, cosine of mx, this by definition is 1 over pi, negative pi to pi, cosine of nx, cosine of mx, dx. It's not too hard to check using basic integral rules that this is 1 if n is equal to m, and it's equal to 0 if n is not equal to m. I think the best way to do this, you may look at this and say, oh, that's a terrible integral. But I think the best way to do that is to actually write cosine of nx as e to the I n x plus e to the minus I n x over 2. And if you write these things with complex exponentials, the integral becomes a lot easier. So also, not only are these vectors orthonormal, but so is the sine and the cosine, or so are the sines. So sine of nx and sine of mx. If I take this dot product, I get 1 over pi. So by definition, I get sine, let's fix that. It's sine of nx times sine of mx, and that is also equal to 0. 1 or 0. 1 if n equals m, and 0 if n is not equal to m. And finally, if I take the integral of cosine of nx times sine of mx, that by definition is 1 over pi, negative pi to pi, cosine of nx sine of mx. Well, that's always equal to 0, because these things are always going to be truly different functions. And let me just say a quick word about this. What the heck is this coming from? It turns out that if you take the function 1 and take the dot product of 1 with itself, what are you going to get? You're going to think you get 1, right? Well, not so fast. So the dot product of 1 with itself, let me just mention that this thing is, let me finish this first. So 1 over pi, from negative pi to pi, times 1 dx. So this is 1 over pi times the integral of 1, so that's x from negative pi to pi. So this is 1 over pi, so easy to make a mistake with this, times 2 pi equals 2. So this is a function v dot v. That is just the norm of the function 1. So yes, with respect to this inner product, it's a little bit weird. A constant function, I should say that's the norm squared of 1, because the norm of 1 is the square root of this. Actually, how about if I... Yeah, that's fine. So the norm of the function, in other words, the norm of the function 1 is the square root of 1 dot 1, and so which is the square root of 2. So you can think of this as 1, which is proper. This is the vector 1, which is properly normalized. Again, this is a little bit of a weird inner product. You know, it doesn't behave the way you would think on this function, but it's magical in what it does. So what this means is that we can, because this is an orthonormal basis, we can take any old function, f of x, and we can write it as a sum of these things. So we can write this thing as n equals 0, I should say n equals 1 to infinity of an cosine of nx plus bn sine of nx. I forgot my n equals 0 term. I'll put it here. For technical reasons that I won't get into, we usually write that term as a naught over 2. I know there's a root 2 here. It's because this thing dot itself. Don't worry about the details. But big idea, that means that any old periodic function we can write using these functions, and these coefficients are just dot products. So to summarize, given any continuous piecewise 2π periodic function, things like a square wave, things like a sawtooth wave, or weird things like this, we can write it using sines and cosines. Again, any musician could have told you that, but what's really great about this is now we have formulas for how to do it. An is just the projection of the function onto the cosine function. It's f dot cosine of x, which in our abstract definition of our inner product is this formula. And bn is just the projection of f onto sine, and that's given by this. And I know it's weird that I have this 2 here. The reason why is because we're slightly cheating by putting a 2 instead of a root 2 here, but it makes this formula also work for n equals 0. So this formula also works for n equals 0. So you only have to remember one formula. So I want to conclude by mentioning that everything we've done so far is for 2π periodic functions, but of course this works for functions of a general period. So if f of x is period 2L, then we can write f of x as a sum of sine and cosine waves that are dilated like this, and the formulas for an and bn are similar. They're just slightly more complicated. We're going to stick with 2π periodic functions because it just makes the math easier. We don't have this L on the bottom, we don't have this pi on the top. These things are a little bit messy enough as is. We don't need to make it more messy by adding in one more thing that can change, which is L.